All right, hello everybody. Coming to you from the minivan this morning. I'm going to talk a little bit about homework number 3. And homework number 3 focuses on normal distributions and z-scores. So I just want to give you the basics of what I expect from this exercise because it's a little bit involved. Okay, so for this homework, what you've got are F0, F1, and F2 measurements from the midpoints of the vowels that you produce for the initial homework exercise. I've got these loaded up on the course website. I don't have internet here in the parking lot of the YMCA. I apologize, but it's okay because we have everything we need on the hard drive of this computer. So this is the data set that you're going to start with. It's basically what you looked at for the last homework exercise, or it's what was generated from homework number 1, and we're still using it, but I expanded upon this a little bit by including these formant measurements here and also F0 measurements. In addition to that, I've put the sex and height of specific speakers in this data set. So for this reason, I'm only using the speakers who both gave me their VOT measurements and also gave me their height measurements in that little background questionnaire I sent you at the beginning of the class. The sex variable is going to come into play as we go through this. You'll see why I'm including that as we go through, but I'll mention, I think there were 8 speakers who gave me all this information from our class, only one of which was male, and we're going to be making comparisons between women and men in this particular exercise. So to make it a little more interesting, I grabbed 2 guys from the last version of this class from a couple years ago, a couple of my former grad students, Lyndon and Dushan. Dushan's still my grad student, just to make the data a little more kind of fleshed out. Okay, so we've got all this data in this particular data set, which you can download from this this link on the website. I've got that listed in the homework if I go back to it. So download the data file from that web link. And I'm not going to say anything further about that other than the fact that, there are different stops and different vowels in here as well because you produce these 5 words for each place of articulation. What do you have to do for this homework assignment? Well, the first thing is I want you to plot all of the vowel formant measurements together in a scatter plot. So part of what you're going to learn here is just how to make a scatter plot in R. And you're going to do this in kind of an unusual way. For those of you who haven't taken much linguistics or phonetics, we do something funny. So, first of all, I guess I'll step back a second and explain to you that we have these different vowels, E, A, A, O, U, as in peel, pale, paul, pull, pool. And they have acoustic characteristics, acoustic features called formants, which I'm not going to go into in detail in this class. But they ascend in frequency. So the lowest formant is called F1, lowest formant frequency is called F1, the second lowest formant frequency is called F2. And for the most part, those 2 formant frequencies will tell you what a vowel is. And you'll see that as you plot these out as you go through this exercise. So these are frequencies in hertz, which is just a kind of standard scientific unit for cycles per second. That's all I'm going to say about that. This F0 measurement is also measured in hertz, but it's something different than the formants. It's about how fast your vocal folds are vibrating. We don't need to worry about F0 really for the moment. We need to worry about F1 and F2. And the funny thing about F1 and F2, if you haven't seen this before, is that when you plot them in a chart, they are typically plotted backwards in sort of reversed orientation from the way you normally make a plot. So to get specific, what I want you to produce is basically, I'm going to give you a specific command for how to do this, but what it will look like is that it'll be a traditional vowel space with F2 on the x-axis, the second formant frequency on the x-axis, F1 on the y-axis, and the scale for each one of those axes is reversed such that F2 values decrease from left to right on the x-axis rather than going up. And then F1 values will decrease from the bottom to the top on the y-axis. Right, so just so you can see that, it's going to be a little bit easier to look at a picture rather than figuring out which direction my hand is waving on this reversed zoom, or it's not zoom, it's ScreenFlow. Anyways, who knows which way my hands are going, it doesn't matter. We'll just look at this in a plot here in R. So I'll start off by saying I've loaded all the data into a data frame called vowels. And this is just from my hard drive here because, again, I don't have internet, but I can still use it. And the way I'm going to plot it is using this plot command. And there's a lot of different little variables in here, or parameters. Got to turn up the heat. There's a lot of different parameters in this plot command. So this first one this is what's going to be on the x-axis, and it's going to be F2. And this is going to be on the y-axis. It's going to be F1. This is an interesting little parameter here, which winds up being really helpful, but it basically tells you what characters to use to plot each vowel. So instead of seeing a dot in the plot, we're going to see the vowel character itself, like E, A, A, O, U, that sort of thing. Xlim is the labels on the x-axis, and by plotting them like this, where I go from the big number first to the smaller number second, it's going to be plotted in reversed order, which is kind of nice. Ylim is showing you what numbers are going to be on the y-axis, and again, going from big to small gets you in the sort of reversed order we're looking for. This X label is just what's going to be labeled on the x-axis. This Y label is just going to be what's labeled on the y-axis. And this is the main label for the entire graph. And then color is what color the little points are going to be in the graph. So having walked through all of that, I'll show you what it looks like and kind of confirm that it does everything I just told you it would do. So all these little points are plotted as vowel symbols like E, A, O, U. We've got, let me resize this a bit so you can see it better. We've got F2 here on the x-axis, and it's going in reversed order. F1 on the y-axis, and again, it's going in reversed order. So the 0, 0 point would be somewhere over here in the upper right-hand corner rather than down here in the upper left. And again, if you want to know the technical reasons why we're doing this weirdness, take my phonetics class if you haven't done so already. That's 341 for those of you who are watching at home. All right, so this basically looks the way we'd expect it to, which is nice. That's just the start of this adventure. Gonna increase the heat here. All right, gets a little bit cold on fall mornings in Calgary, Alberta. All right, the trick with this graph is that I would like you to plot the formats produced by men and the formats produced by women in distinct colors. So note that you can add points to a pre-existing scatter plot in R with a command like the following. So the reason I'm focusing on this male-female difference is because it is relevant to format frequencies. There's technical physical reasons behind this, but basically men have longer vocal tracts, and that makes their format frequencies lower. In general, not always. Okay, so what we're going to do here is going to subset out the male vowel data by grabbing all of the speakers whose sex is M. And now what I can do is add to that original graph by using the points command. So I create a graph, a scatter plot by using the plot command, and now I'm going to add to it by using the points command. So what I've got here is just the subset of male vowels, and I'm going to plot their F2 on the x-axis, and I'm going to plot their F1 on the y-axis. I'm going to use the relevant characters from that data set using just the vowel variable there, but I'm going to plot them in blue. So the originals were all plotted in red, but this time I'm going to plot these in blue. It will overlay on top of what we've seen before, but you won't notice it because the blue is going to be on top. And so if I do that, what we'll see is this interesting little difference we get between male and female vowels. It's just an acoustic difference. So they're clustered more closely to the 0, 0 point because their format frequencies are lower. Yeah, and so these are all the male vowels in blue, and then because by default the ones remaining that are not in blue, the red ones, are the female vowels. Yeah, so that's one way to distinguish between those. Right, and this is what it looks like in sort of absolute acoustic frequency terms. The fun part of this is that we're going to tweak that a little bit to see if those differences remain when we normalize the data. Okay, so I'm also going to add that you can add a legend to this. This is more for practical purposes if you ever want to actually create one of these yourselves for whatever report you're making in your own research or your own homeworks, what have you. You can add a legend like that for this. There's a variety of different options you have here, so I'm putting that one on the bottom left. And this just says these are the names of each row in the legend, and this is the colors that I want to use for the specific legend. You can tweak with that however you want. You can tweak with the colors. I don't care which colors you use for this. It's up to you, but just so you know, these are just the practicalities of how to make a graph like this in R. And I've also got a link here, which I can't link to, but there's a huge array of colors that you can use in R. I know a lot of people like to play around with those because it's fun to make pretty pictures. Okay, so what we are going to do, that's task number 1. Just create this graph or a graph like it. Then for task number 3, we're going to create a different graph. But to do task number 3, we have to do task number 2 first. Okay, what do we do for task number 2? I want you to normalize each speaker's format measurements by converting them into z-scores specific to each speaker. All right, so we're going to use this term fairly often in this class, or you'll hear it used fairly often in the world of linguistics and other social sciences, but normalizing data in this context will specifically mean that we're going to convert some scores, some raw scores, into z-scores. So in a sense, I guess I should step back. On the more general sense of normalize is to sort of put measurements like on a level playing field, so that they don't depend on things like maybe whether a speaker is male versus female. So normally when we listen to somebody speak and we hear them say a word like peel, like we on one level can say, well, that's, sounds like a male speaker or a female speaker, but there's another level where it's sort of like, oh, that's the word peel, and it doesn't really matter if it's being said by a male or a female speaker. They're both like saying the same thing, right? So we're trying to get to that point where it's just like we're at the peel level, we're at the linguistically meaningful level rather than the like what sex is that speaker level. So this is going to be one approach to doing that with vowel format measurements. It's called the Lobanov method of vowel normalization, after a researcher named Boris Lobanov, who described this approach in a short paper back in 1971, and will live forever because of that. There are different ways to do this, but we're going to do this one because it's kind of the easiest one. It also just like focuses on using z-scores, which we have learned about in this class quite recently. But this method recognizes that every speaker has a unique F1 and F2 range, and thus the z-scores for any speaker's formants can only be calculated with respect to that unique vowel space. Okay, so we're going to normalize by individual here. So I'm going to walk you through a kind of basic way to do this. We're going to extract Summer's format measurements out of the data frame like this, and sorry for volunteering you like this, Summer, but your last name is the first in the alphabet because it's Abdallah. Hopefully you don't mind, Summer. Okay, here we go. We're going to extract, Summer's measurements out. I guess I should tweak that. I'm going to change this in the homework so I don't confuse everybody when you're doing it at home yourself. Just using a different name for the data frame, but we've got Summer's data in her own data frame now. We're going to summary Summer, and we're going to get this. Okay, it looks good. At least it's functional. And what I want to do is create normalized F1 and F2 scores. So we're going to do that by creating z-scores like we talked about in the lecture. So, and we're going to do it by format for Summer herself and only herself. So what I need to kind of think about are what are Summer's mean and standard deviations for both F1 and F2, and we're going to treat them separately. So for every single F1 measurement, actually maybe I'll go back. There's only 15 of these. Right, so we've got 15 F1 measurements and 15 F2 measurements for Summer for these various productions of these words. I don't think I said this before, but I'm only looking at the first repetition of each word for Summer's data, for everybody's data for that matter. So there's not that huge set of data that we had before. And what I want to do, can I just do this? Yeah. So for each one of these 15 measurements for F1, I'm going to subtract the average F1 measurement for Summer. So R will automatically calculate on the fly the mean of these F1 measures and also its standard deviation. So that's basically going to give me a z-score for every single F1 measure. So let me hit return, and we'll take a look and see how this works. And that's just a vector, so it's not organized in data frame fashion. So it's kind of hard to match it up, but it's basically saying like the first one, 434 hertz, it has a z-score of negative 1.05, so it's less than average. Maybe we can also do this. So the average F1 for Summers vowels is 540 hertz, so that kind of stands to reason. That's less than that, so it's going to have a negative z-score. Maybe we can look at a positive one, so 3 away. That's probably for right? Call. This one, 692.6, has a z-score of 1.52 because that's on the high end. Okay, so these are our normalized F1 measures. We can also get normalized. Oopsie, didn't want to do that. So let's do norm F2. We get the same sort of thing, and that's basically going to normalize these F2 measurements by converting them into z-scores. Okay, so what I want you to do is to do that for all 10 speakers in the data file. I've got this note here about make sure that each speaker's z-scores go into different vectors, i.e. not everyone's z-scores can be labeled norm F1 or norm F2. And I've got some more specific information about how to do that down here, but I'm not going to get to that yet because I want to go straight to task number 3 so you know what we're trying to accomplish here. Okay, so what I want you to do is plot all the speakers' performance z-scores together on the same scatter plot. So before, we plotted everybody's vowel measurements on the same scatter plot, but we were plotting acoustic measures in hertz, in raw acoustic physical units. What we want to plot on the second plot are z-scores. So on the x-axis, we're going to plot z-scores for F2, and on the y-axis, we're going to plot z-scores for F1. But it's going to be a little bit weird, right? Because, Summer's z-scores are going to be generated in a slightly different way than Charles's z-scores because they both have different mean F1s and different standard deviations for the different formats, right? But I still want you to just get those z-scores and plot them on the same graph. That's effectively what normalization does. Okay, so plot the male produced z-scores in one color, female produced z-scores in a different color, and just use the same color coding scheme you use for the plot in task number 1. And I'll show you an example here of what this will look like when you do it for Summers values. And yeah, so this is basically everything we saw before. It's going to erase our previous graph. Sorry about that. But basically everything looks the same except we've got norm F2 on the x-axis, norm F1 on the y-axis. I'm changing the limits of what's plotted on the x and y axes from rather than these big numbers that we used for acoustic frequencies. These are going to be plotted with respect to z-scores. We've got a z-score of 3 on the sort of high end and a z-score of -3 on the low end for both dimensions. We can also kind of normalize that way, I guess you could say. And I just changed the labels a little bit to say we're plotting z-scores now rather than hertz. Okay, so we do that, and voila, this is what Summer's z-scores look like. But I don't want you to just stop there. I mean, they're all pretty much in the right spot and they look fairly consistent, right? So I don't want you to stop there though. I want you to add everybody else's z-score format values to the same plot. And then, plot women's in one color and men's in the other. And you can add a legend if you want, just to make it clear. But yeah, you have 10 different speakers to do that for, so that will take you a little while. And then once you're done with that, I want you to answer these questions. So how does the resulting normalized z-score format plot look different from the original format plot you put together? You'll probably notice a difference. What differences do you observe between the male and female vowels, if any, in the two plots? Separate question. What do the differences between vowel formats represent in the first unnormalized plot? What do the differences between z-scores represent in the second normalized plot? These are just kind of like confirmation questions to make sure that you can tell me that you understand what you're actually doing here, because I don't want you just following instructions and not actually thinking about the meaning of what's going on. Okay, so as tempting as that might be. So, right, there's also another set of questions here. Consider the z-scores you calculated for the various vowel format measurements in task number 2. What percentage of format measurements fall within 1 standard deviation of the speaker's means? What percentage fall within 2 standard deviations of the speaker's means? Do you think these format measurements are normally distributed? Why or why not? Okay, so this is kind of a different issue, which is more about the shape of these distributions once they're converted into z-scores or not converted into z-scores. I'm going to pause on that for a second and just make really clear. You're going to create 2 different graphic plots, 2 different format plots. one where things are plotted in acoustic hertz on both dimensions, and the other where they're just plotted in z-scores. That's kind of the primary task you're doing here. To get to the second one, though, you're going to need to do this normalization process in task number 2. And then once you get those two plots, you're going to answer these questions. You can answer these questions before you even get to the plots, though, because it's just about the data that you have. So let me walk you through these other R instructions just to kind of like help situate you in this task. Sorry, constant adjustments of temperature. Yeah, so this will help you just with the mechanics of doing this exercise. So let's go back to summer's data. So we have summer's data looking like this. So just we're extracting out the individual rows that have summer's vowels in them. Maybe I'll do it this way. And sorry about the beeping. What I want to do is add those normalized measurements to this mini data frame for summer alone. And I can do that by using this cbind command. Basically, this means column bind is one way to look at it. So what I'm going to do is I'm going to take this data frame and add to it this column. So this is just a vector of values, as we've seen before. It's just these raw numbers, not organized in a table or in a data frame. That's going to be the first column I add, and this is going to be the second column I add. So if I hit return there, and I look at summer 2, what I see is I've got the normalized measurements over here, these next two columns in the data frame, which is great, because now I know directly that 434 corresponds to a z-score of negative 1.05, and then 2585 corresponds to a z-score of 1.33, so on and so forth. And these are normalized with respect to their specific format measurements, right, F1 and F2. Okay, so that's great. And I can give you this command as well, which is relevant to answering these questions. So you can determine how many of summer's normalized F1 values are within one standard deviation over mean F1 with this command. So it's n row, which is basically counting the number of rows in some data set. So what we're going to do here is we're going to take a subset out of this data frame here, and these little qualifications here will tell me only tell me how many rows have a normalized F1, which is both less than 1 and also greater than negative 1. So within one standard deviation of the mean. And we can kind of go through here and count if you want, but I'm just going to execute the command, and it says 10. So there's 15 rows here altogether, and it's basically saying there's 5 of these which are either less than negative 1 like this or greater than 1 like this. So we've got 1, 2, 3, 4, 5. The rest are 0 point something, right, or negative 0 point something. So that seems to be working correctly. We can also try it with F2 just so you see how it works. Like that says 11, so there should be 4 that start with 1 or negative 1 here. 1, 2, 3, 4, so that looks right? That is a way to answer these questions. So what percentage of format measurements fall within one standard deviation of the speaker's means? What percentage fall within 2 standard deviations of the speaker's means? Now that you know how the basics of how this works, I think you can answer these questions pretty easily. And then you have to think a little bit about how to answer this one. Do you think these format measurements are normally distributed? Why or why not? I'm going to leave that one up to you. All right, so sorry this is going on so long. I do want you to be able to think about these things and know what's going on, though, so that's why we're doing this exercise. Okay, so let's create another subset of data for a different speaker. We'll go to Katya's data, and we'll subset it out like this. Yep, sorry, I got to change that as well. Sorry. Vowels, not formats. What was I thinking? Okay, there's Katya's data. Looks like that. It doesn't have those extra columns, though, so I can't sort of like compare it up with what we were doing here with summer. So I'm going to create normalized measurements for Katya as well. We'll get those two, and then we're going to add them to Katya's data in Katya 2. And it'll look like what we saw before with summer. But now we've got, Katya 2 in one data set or data frame, and then summer 2 in another data frame. If I want to combine those together, I can use the rbind command. So before I was combining columns with the cbind command. Now I'm going to be combining rows with the rbind command. So normalized is going to be a new data frame, which has Summer's data in the first set of rows and then Katya's data in the second set of rows. And then we're just going to look at it so that you can see that I'm not lying to you. And lo and behold, there it is. All this good stuff, right? So this is a way to sort of add these normalized values and columns to the data frame in R. It may be a little bit clunky, but it's also going to make it easier for you to sort of do calculations like this, right? Basically, if you're looking for a way to do this, this is how it's done. And as usual, when you send in your homework to me, make sure you send in, the commands you used in R to make the magic all happen. If you want to use some, other like program out there, like Excel or what have you, you can do that if you think it's going to make your life easier, but still send me the R commands you use to like actually do this exercise, whatever they happen to be, just so I can figure out what happened if things don't go the way we planned. Let's put it that way. All right, so that's all I'm going to say about that. There's also a fourth task to this, not to add too much on here, but again, hopefully it'll be the reason why it is relevant will become clear as you go through it. All right, so for this, I want you to normalize the VOT measurements in the data file by stop place of articulation. So let's go back to our originals here. The vowels data set has measurements of F1, F2, F0, which we're not playing around with today, but also VOT. So we've seen VOT before, and we did some plotting of VOT measurements in the last exercise, which is great. But this is going to be a little bit different because before we had 3 repetitions for each item. Here we only have 1. We also have a couple new speakers in this data frame and a few that we're missing as well. So it's slightly different data. So part of this is going to be a repetition of what you did before, but then we're going to add something new. Okay, so the part that's kind of repetition is task 4A. So for this, I want you to produce another box plot of the stops raw VOT by place of articulation. And this is going to be basically what we saw before. Maybe I can bring out what we did so you can see it again, just to make it clear what I want these homeworks to look like. Right, so I don't have this for everybody, but I have it for individual speakers. So we'll pick on Andrea and her VOT by place of articulation graph looks like this. So this is basically what I want you to do again. You're not doing it for an individual speaker, though. You're doing it for everybody. So for the entire data set, plot VOT by place of articulation, PTK. So from the front of the mouth, P to the back, K there. And it'll look a little bit different from that, right? Okay, so, and you might notice, this isn't always the case, but the VOT tends to increase as place of articulation moves further back in the mouth. And that's generally what's happening here with Andrea's VOT data. Okay, that's the raw data. This is plotting VOT just in milliseconds. What I also want you to do is normalize that data, but you're not going to normalize it by speaker in this case. What I want you to normalize it by is place of articulation. So before, when we were normalizing like Summer's F1 measurements, we were looking at Summer's mean F1 and we're looking at Summer's standard deviation of F1, but I don't want you to do that by individual speaker. I want you to do it by place of articulation. Yeah, when you normalize this data, calculate the z-scores relative to each place of articulation. That is, normalize the k-VOTs by the mean VOT for k and the standard deviation of k-VOTs. Hopefully that makes sense. But basically, rather than having Summer here, you're going to have k, your k data set here. So you're going to look at the mean VOT for k, the standard deviation for k, and then like the individual k-VOT measurements here, right? Hopefully that makes sense. We're going to do that for each of the 3 different places of articulation. And then once you've got those normalized measurements that are normalized by place of articulation, produce another box plot of the z-scores. And the only thing that's going to differ there really, you're not going to change anything on the x-axis because we're still playing around. Come on now. Well, that doesn't work. we're still going to be playing around with the 3 places of articulation, but will change. What will change is on the y-axis. So instead of plotting the raw milliseconds for these measures, you're going to be plotting the z-scores on the y-axis. Make sense? So you'll wind up with 2 different plots, one with the VOT in raw milliseconds and another with the VOT in z-scores. On the x-axis, they're going to be the same, place of articulation. And then answer the following questions. Does there still seem to be an effective place on VOT once you've normalized the data in this way? Why or why not? And then also you can answer these sort of technical questions again, like for each place of articulation, how many VOT measurements fall within 1 standard deviation of the mean? How many fall within 2? Do you think these VOT measurements are normally distributed? Why or why not? We kind of looked at that before in the last homework. This is a way to sort of quantify the normal distribution question a little more precisely, but still answer it. And you kind of maybe will know where the answers are going based on what happened in the last homework, but still I want you to think about it again. And then also think about it with respect to what we did in the first sort of half of this exercise. Consider both of the data sets you've worked with for this exercise. Which data seem to be more normally distributed? The formant measurements or the VOT measures. So just to point out, a lot of people noticed this in the previous homework, but certain distributions can be closer to normal than others. Like even if none of them are like obviously normal, some of them look a little closer to the pattern than others, right? And you might observe this as well with this VOT and formant measures in this data set. And then you can think about like why might one of these sets of data be more normal than the other. That's more of like a philosophical question. So, there may or may not be a right answer to that. I'll just let you think about it. Okay, last of all, write up your results in a clear and concise report, and then upload your report and all the relevant plots and files and your R consoles to the Dropbox on D2L. This is a kind of a crucial part. This doesn't have to be super long or anything. It just needs to be comprehensive. Just like explain to me what you did. It's the easiest way for me to kind of give you feedback and also understand, make sure that you understand what you were doing as well. All right, it looks like I am done for today. And let me know if you have any questions about that. See you next time.